Hello guys, today we're going over problem 1 in the Polynomials in the AIME problem set, and this is also linked to the playlist. So find the sum of the 20th powers of the roots of z to the 20 minus 19z squared plus 2 is equal to 0. So let's say the roots are r1, r2, to r20. Well then, r1 to the 20th minus 19r1 squared plus 2 is equal to 0. And we want to find r1 to the 20th plus r2 to the 20th plus to r20th to the 20th. And using this equation, we see that r1 to the 20th is equal to 19 r1 squared minus 2. Plugging this in for all of them, we get 19 times r1 squared plus r2 squared plus to r20th squared minus 40. And this is r1 plus r2 plus to r20th squared minus 2 r1 r2 r1 r3 and using Vieta's formulas, we see that both of these are equal to 0. So our answer is just negative 40. Thanks for watching. Hello guys, today we'll be doing problem 2 in the Polynomials in the AIME problem set, and this is also going to be linked to the playlist. So find 2 plus r times 2 plus s times 2 plus t times 2 plus r u if r, s, t, u are the roots of this polynomial. And basically, we can turn this polynomial into root form, which is, in other words, just this. And basically, plugging in negative 2 gives us and we can factor out a negative 1. And now we see this is the equation we want. It worked out perfectly. And so, f of negative 2, we have to calculate that. So 3 times 16 minus negative 8 plus 2 times 4 plus 7 times negative 2 plus 2. This gives us 48 plus 8 plus 8 minus 14 plus 2. 48 plus 4 is equal to 52. And so 52 divided by 3 is our answer. Thank you for watching. Hey guys, today we're going through problem 3 in the Polynomials in the AIME problem set. And this is also going to be linked to the playlist. So let RST be the solutions to the equation 3x cubed minus 4x squared plus 5x plus 7 is equal to 0. Find r squared plus s squared plus t squared, r cubed plus s cubed plus t cubed, 1 over r plus 1 over s, and 1 over t. So first of all, section A, let's find r squared plus s squared plus t squared. And this is easy. This is just going to be r plus s plus t squared minus rs plus st plus rt. Using Vieta's, we see that this is just 4 over 3 squared minus 5 over 3. Sorry, there's a 2 in front of this. Minus 2 times 5 over 3. This gives us 16 over 9 minus 10 over 3, which is negative 14 over 9. Section B, r cubed plus s cubed plus t cubed. So what we could do is we can do a similar technique to what we did in problem 1. We can plug in r, so 3r cubed is equal to 4r squared minus 5r plus 7. And seeing this, r cubed is equal to this over 3. So what we get is 4 times r squared plus s squared plus t squared minus 5r plus s plus t plus 21 all over 3. And using the above, this gets us negative 56 over 9 minus, using Vietas, 20 over 3 minus 21. Also, this is a minus. Sorry, guys. So, subtracting this all over 3 gets us our answer of negative 305 over 27. And lastly, for section C, find 1 plus r over plus 1 plus s plus 1 plus t. So if we multiply rst on both sides, we get rs plus st plus rt over rst. And using Vietas, we get 5 over 3 over negative 7 over 3, which is just negative 5 over 7. Thank you guys for watching, and I'll see you in another video. Hello guys, today we're going for problem 5 in the Polynomials in the AIME problem set. And this is also 1977 AHSME problem 28, I think. So let g of x equal x to the 5 plus x to the 4, x cubed, x squared, x plus 1. What is the remainder when the polynomial of g of x to the 12th is divided by the polynomial g of x? We notice x to the 6 minus 1 is equal to negative x minus 1 times g of x, or x to the 5th plus x to the 4th plus x to the 3rd. And this is just the sum of powers technique. So we know that x to the 6th minus 1 is equal to 0 mod g of x. So x to the 6 is equal to 1 mod g of x. So if we plug in x to the 12th, we get x to the 60 plus x to the 48 plus x to the 36 plus x to the 24 plus x12 plus 1. And we want to find this mod g of x. And since x to the 6 is 1 mod g of x, this is just 1 to the 10 plus 1 to the 8th plus 1 to the 6 plus 1 to the 4 plus 1 squared plus 1, or just 6. Thank you for watching. Hey guys, today we'll be going over problem 6 in the Polynomials in the AIME problem set, or 1980 AHSME problem. This will also be included in the playlist. So the polynomial x to the 2n plus 1 plus x plus 1 to the 2n is not divisible by x squared plus x plus 1 if n equals one of these numbers. So first of all, we notice that x cubed minus 1 is equal to x minus 1 times x squared plus x plus 1. So x cubed is equal to 1 mod x squared plus x plus 1. And this is significant because now, instead of doing x to the 2n, we can do x to the 2n mod 3. And you might be like, well, why mod 3? So basically, if n is, let's say, 4, then x to the 2 times 4 can be written as x to the 2 times 3 plus x to the 2 times 1. And this is just 1, because x cubed is 1. So that's why we take mod 3, to make things easier on ourselves. So now we have just a couple cases. Case 1, n is equal to 0 mod 3. This means that x to the 2 times 0 plus 1 plus x plus 1 to the 2 times 0, which is just 1 mod x plus x squared plus x plus 1. So this does not work. N is equal to 1 mod 3. Doing this, we get x squared plus x plus 1 squared plus 1. Evaluating this, we get x squared plus 2x plus 1 plus 1, or 2 times x squared plus x plus 1. So this is 0 mod 3. 0 mod x squared plus x plus 1. And lastly, n is equal to 2 mod 3. Doing this, we get x to the 4th plus x plus 1 to the 4th plus 1. And, well, this can be written as x to the 4th plus x to the 4th squared plus 1. And we see this because this can be turned into x plus 1 because a number cubed is just 1. So doing this is just, cut. We have x to the 4th plus x plus 1 to the 4th plus 1, which is just x plus 1. We have x to the 4th plus x plus 1 to the 4th plus 1. And basically, evaluating this, we get x to the 4th plus x squared plus 1, which is 0 mod x squared plus x plus 1. After simplifying, of course. So we see that the only number n can be is 0 mod 3, and the only number here that is why 3 is c. So that is our answer. Thank you for watching. Hey guys, today we'll go over problem 8 in the Polynomials in the AIME problem set, or 1988 AIME problem 13. So find a if a and b are integers such that x squared minus x minus 1 is a factor of ax to the 17 plus bx to the 16 plus 1. So let's call r a root of this. And if it's a root of x squared minus x minus 1, it's also going to be a root of this because x squared minus x minus 1 is a factor of ax 17 plus bx 16 plus 1. And so if r is a root, then r satisfies this equation, which means that r squared is equal to r plus 1. So using this to our advantage, now we have the equation ar to the 17th plus br to the 16th plus 1. Plugging this in to this equation, we get ar to the 15th times r plus 1 plus br to the 16th plus 1. Now, simplifying, we get ar to the 16th plus ar to the 15th plus br to the 16th plus 1. Simplifying again, we get a plus b r to the 14th, r plus 1, plus ar to the 15th. Simplifying again, we get 2a plus b r to the 15th, plus a plus b r to the 14th, plus 1. Now, doing it again, we see that 2a plus b r to the 13th, plus 2a plus b r to the 13th times r plus 1 plus a plus b to the r 14th plus 1. Simplifying, we get 3a plus 2b r to the 14th plus 2a plus b r to the 13th plus 1. So we see that these are just Fibonacci numbers. So at the very end, we see that we're going to have the Fibonacci, the 17th Fibonacci number times a plus the 16th Fibonacci number times r plus f of 16a plus f of 15b plus 1 is equal to 0. So from here we see that this has to be equal to 0 and this has to be equal to -1 for this to be true. So the 17th Fibonacci number, 1598, 97a plus 987b equal to 0, and this gives us 987a plus 610b is equal to -1. Solving these two equations, we get that a is equal to 987. Thanks for watching. See ya. Hey guys, today we're going over problem 10 in the Polynomials AIME problem set, and this is also a problem in AOP's intermediate algebra. So let p of x be a polynomial such that when p of x is divided by x minus 19, the remainder is 99, and when p of x is divided by x minus 99, the remainder is 19. What is the remainder when p of x is divided by x minus 99 times x plus 99? So I believe using the division algorithm, we can write this as p of x is equal to x minus 19 times quotient of x plus 99. So this is the quotient, what we're dividing by, the remainder. And writing in a similar fashion, we can write this as x minus 99 times a different quotient plus 19. And we know that p of x is equal to x minus 19, x minus 99 times a third quotient plus some remainder. And so how we find this is we plug in x equals 19 and x equals 99. So p of 19 is equal to 99. And p of 19 in this equation is equal to ax plus b. Sorry, not ax plus b, 19a plus b. So 19a plus b is equal to 99. And p of 99 gives us 99a plus b is 19. So subtracting these two equations, we get that 80a is equal to negative 80, or a is equal to negative 1. And if a is equal to negative 1, b is equal to 99 plus 19, which is 118. So the remainder is negative x plus 118. Thank you for watching. Hello guys, today I'm going over problem 11 in the Polynomials and AIME problem set. So this is 2016 AIME 2 problem 6. So for polynomial p of x, which is equal to 1 minus 1/3 x plus 1/6 x squared, define q of x as p of x times p of x cubed times p of x to the 5th, which is also equal to the summation of 50 I is equal to 0 ai xi. Then the sum of the coefficients, sum of the absolute value of the coefficients is m over n. Find m plus n. So we can start off by seeing that p of negative x is equal to 1 plus 1/3 x plus 1/6 x squared. So q of negative x is just going to be equal to p of negative x, p of negative x cubed, which is at the end of the day is also negative. So q of negative x is equal to 1 plus 1/3 x plus 1/6 x squared, and then 1 plus ... But all these terms are positive coefficients. So we know that q of x is going to have odd terms negative and even terms positive. Essentially plugging in x equals negative 1 into this entire equation. And if we do, we see that this is so positive, 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 and negative, negative, negative. So, sorry, exponents. So now we see that q of x is equal to, according to this summation right here, q of x is equal to a0 plus a1x plus ... to a50x to the 50. And if we plug in q of negative 1, we see that we get a0 minus a1 plus ... plus a50. And well, we know that q of x is odd exponents negative, even terms positive, so we can write q of x as a0 minus a1x plus dot dot dot. And we see that the coefficients are just q of negative 1. So what is q of negative 1? Q of negative 1 is equal to p of negative 1 to the 5th power. And what is p of negative 1 to the 5th power? 1 plus 1/3 plus 1/6, which is 3/2. And so q of negative 1 is just 243 over 32. And n plus n is 275. Thank you for watching, and if you enjoyed this video, watch another one and subscribe to our channel. Peace. Hello guys, take over problem 12 in the Polynomials in the AIME problem set. So 1984 use model problem 1. In the polynomial x to the 4th minus 18x cubed plus kx squared plus 200x minus 1984 is equal to 0. The product of two of its roots is negative 32. Find k. So using Vieta's, we could see that negative, positive. So we could see that the other two roots multiply to negative 1984 over negative 32. In solving this, we see that the other two roots multiply to 62. So we can write the polynomial as x squared plus ax plus 62, x squared plus bx minus 32. So we have these two equations. And now we see that negative 32a plus 62b. So this is the x term. The x term is 200. And now the x cubed term, which is this and this, which is just a plus b, is negative 18. So solving these two equations and multiplying 32 on both sides, we get that a is equal to negative 4. We get that a is equal to negative 14 and b is equal to negative 4. So p of x is equal to x squared minus 14x plus 62 times x squared minus 4x minus 32. And so we want to find k, and k is just 62 plus 14 times 4 minus 32. And this, and this. And so 62 plus 56 minus 32. Our answer is 86. Thank you for watching, and if you enjoyed this video, make sure to watch another one and subscribe. Peace. Hey guys, take over problem 14 in the Polynomials in the AIME problem set, or aka 2014 USMO problem 1. So let a, b, c, d be real numbers such that b minus d is greater than or equal to 5, and all of zeros x1, x2, x3, x4. Polynomial p of x is equal to x to the 4th plus ax cubed plus bx squared plus cx plus d are real. Find the smallest value of the product, and that. Okay, so first we do difference of squares. And the reason we do this is we want to break down what we're trying to find, because right now it doesn't really seem feasible. And well, if you notice, all of our solutions are in the form x minus r. And you can see that the polynomial is just equal to x minus r times x minus s times etc. And so what we can say is that these highlighted ones, so namely these four, this is just p of negative I and p of negative I. And these highlighted ones are p of I. So now that we've seen this this is just p of negative I times p of I. And so plugging in, we get I to the fourth, which is 1, plus I cubed is just I, but it's p of negative I, so minus b minus ci plus d. And the second one is just reversed coefficients. So we want to evaluate this. So we first take all the I terms, which is 1 minus b plus d plus a minus ci. So this is our expression right now. And doing difference of squares, this is just 1 minus b plus d minus a minus c squared plus a minus c squared. So now we have to use our condition that b minus d is greater than or equal to 5. And this is just 1 minus b minus d. And b minus d is greater than or equal to 5, so the smallest value you can take is 5, so 1 minus 5, which is negative 4. And so negative 4 squared plus a minus c squared. And all squares have to be greater than or equal to 0, so the smallest value that's going to attain is 16. Thank you for watching. Hope you learned something today. And if you enjoyed our videos, please consider subscribing. Peace. Hey guys, take over problem 15 in the Polynomials in the AIME problem set, or 2011 AIME 2 problem 9. So let x1 to x6 be non-negative real numbers such that x1 plus x2 plus all the way to x6 is 1, and that sum is greater than or equal to 1 over 540. Let p and q be positively relative prime positive integers such that p over q is the maximum possible value of that sum. Find p plus q. Straight off the bat, we don't really notice anything particular about this sum, but we do notice that if we add these two together, we might be able to factor it. So we add them together. And adding them together, we see that we get x1 plus x4, and we have x3, x5, x3, x5, x2, x3, x2, x3, x2, x6, x2, x6, and x5, x6, which is right here. We can factor this even more as x2 plus x5 times x3 plus x6. But to make sure it's still our original sum, we subtract 1 over 540. So this is our original sum. And we might be like, why do we subtract 1 over 540? We want the maximum. So we want to subtract as least as possible. If we have 5 apples and we want to maximize it, we don't want to subtract anything. So we subtract the minimum, which is 1 over 540. So we could use AIME-GM. And what AIME-GM would do is it makes sure that this, so x1 plus x4 times x2 plus x4, x5 times x3 plus x6 is less than or equal to x1 plus x2 plus x3 plus x4 plus x5 plus x6 over 3, which is the AIME, and this is a cube root GM. And well, we can just move the cube root to the other side, and this is our equation. So we know conveniently that this is 1, as seen up there. And so this is less than or equal to 1 over 27. And so the maximum is 1 over 27. So 1 over 27 minus 1 over 540 gives us 19 over 540. And so adding these together, we get 559 as our answer. Hope you guys learned something new today. And if you liked my videos, make sure to hit the subscribe button. Peace. Hey guys, so you go over problem 16 in the Polynomials in the AIME problem set, aka 2010 AIME 1 problem 9. So let A, B, and C be the real number solutions of the system of equations x cubed minus xyz is equal to 2, y cubed minus xyz is equal to 6, and z cubed minus xyz is equal to 20. The greatest possible value of a cubed plus b cubed plus c cubed can be written in the form m over n, where m and n are relatively prime positive integers. Find m plus n. So we have three equations. So we start off by adding them and multiplying them. So step 1, we add. If we add all three of them, we get x cubed plus y cubed plus z cubed is equal to 28 plus 3xyz. So not much. Section 2, we multiply. And if we multiply, we get x cubed, y cubed, z cubed is equal to 2 plus xyz, 6 plus xyz, 20 plus x plus y, xyz. So, just to make things easier on ourselves, let's set this as a, for example. So, we see that now we have a quadratic. Sorry, not a quadratic, a polynomial. So, a cubed is equal to, let's factor this. Let's multiply this out. So, we get a cubed plus 7a squared plus 43a plus 60. And so 7a cubed squared plus 43a plus 60 is equal to 0. Now we use the quadratic formula. 43 plus minus square root 43 squared minus 4 times 7 times 60 all over 14. And so after we solve this, we get a is equal to negative 15 over 7 or negative 4. And keep in mind, we want to maximize this, which means we want to maximize xyz, which means we want to maximize a. And so, And so this is maximized. And so if we plug this into our original equation, 28 minus 45 over 7 gives us 151 over 7, which gives our answer to be 158. Thank you for watching. Hope you guys learned something new while watching this video. And if you like our videos, please subscribe. Peace. Hello guys, so you go over problem 17 in the Polynomials and AIME handout, and aka 2005 AIME 1 problem 8. So the equation 2 to 333x minus 2 power plus 2 to the 111 times x plus 2th power is equal to 2 to the 222x plus 1th power plus 1 has 3 real roots. Given that their sum is m over n, find m plus n. So first of all, let's simplify this. We see that 2 to the 111x is in all three coefficients, so we can set y as 2 to the 111x. So we get y cubed over 4 plus 2y is equal to 2y squared. Also, sorry, this is not 2, it's 4, because plus 2, plus 1. And multiplying by 4 and putting everything on both sides, we have y cubed plus minus 8y squared plus 16y minus 4 is equal to 0. And from here we see that y1 times y2 times y3, aka the roots of this equation, multiply to 4.